And we are back for another video. Today we're talking about how to apply what we've been learning about polynomials and other functions when it comes to applications. Specifically, we're looking here at how we can model real-life data and figure out what function best models that data. So anytime you're dealing with modeling, just like we'll be doing in the SACs, it's quite useful to come up with some kind of simple mathematical function that you can use to represent your data so that then you can make predictions about the future. So for if you have access to a CAS calculator, the best way that you're going to be doing this is using the statistics screen over here. And throughout all of this chapter, I'd recommend just using statistics. And also for the purpose of your SAC, you'll also need to know how to do this. So it's important for us to be aware. So I've listed out the instructions here. I'll demonstrate this to you in a minute. First, you go into statistics, then you enter your data. So statistics looks like this. You enter your data into list 1, that's your X values, into list 2 is your Y values. Then you're going to set the graph. So you click this button up here, set the graph. We need to make sure this button is always unticked before we do whatever we want to do. And then we're going to go to this button here. I think it'll come up with settings. So yeah, set graph settings, select what type of graph you're going to be representing. We're going to be building scatter plots, and then we're going to represent that information by creating a regression line. All right, so the step-by-step instructions are just here. To get the regression line, you're going to click Calc, then you're going to click regression, and then you're going to select, based on what your data looks like, what type of regression line you think will best model that data. All right, so I'll get back out of this, scroll down. So for example, if we have this is our data sets over here, we can see that the regression line, well, it does look like this is a linear graph. It's kind of difficult to tell if it is exactly going to be a linear graph. It could in fact be like some sort of polynomial that goes like that. It could go like this. It's not very clear. But if we want to make a prediction, we're going to think, okay, that kind of looks like that it's a linear line. Let's see how well that regression line models things. So we create we'll use our calculator, we'll create a regression line like so, also known as a line of best fit. Basically, you're just going to draw a straight line through the data, and you're going to make sure that roughly half of each of the data points is on either side of that line, or that the line goes straight through the middle of where the data is. So if you do it by hand, it's a bit hand wavy, but if you do it using the calculator, it'll be a little bit better. The calculator will give you something called an R-squared value. The closer that is to 1, the better a line of best fit this is. So for example, if all of those data points lie on the same straight line, then the R-squared value will just be 1. I'll show you what I mean. So for example, if I go, let's just choose a bunch of numbers, and let's say this is a linear line. So let's say it's going to be going up by 2, sorry. Okay, so we've got this data set. Let me graph that for you. It looks like this. You can see all of the data is in a straight line. If I go Calc Regression, Linear Regression, and click OK, you can see here it's given me an equation. It looks like the equation is y equals 2x, b is 0. And you can see this number here, r squared, is equal to 1. So because r squared is equal to 1, this regression line perfectly models my data because I've given it very ideal data in that case. Okay, now there's a couple of other words that might be useful for you to be aware of. These words being extrapolation and interpolation. So these words, extrapolation, this is basically when we're looking at data outside of, well, information outside of the data set. So say, for example, you have data on weather, and this data ranges from, say, January to March. I've just chosen those kind of arbitrarily. So we've collected data from January to March. If I want to make a prediction about the future, say, what's the weather going to be like in October, I don't have data that goes all the way up to October. So what I'm doing is I'm extrapolating on what we know, and making a prediction about the future. However, let's suppose I have information from January to March, but I don't have information about what happened on February the 5th, some particular dates in February. Let's make it February the 6th, so it's today. So I haven't gathered data on what the weather was like on today, on the February the 6th, or whatever it might be, some day in this period over here. I look at this data, it looks like the temperature will be roughly here, where the regression line is. What I'm doing now is I'm interpolating the data because I'm making a prediction about something that lies within my data set. So that's the difference between extrapolation and interpolation. Generally, interpolation is considered better because, like I mentioned, like we're looking at data that we know something about, whereas extrapolation, we're making a prediction. We're just assuming that the trend will continue leading into the future, not necessarily always going to be the case. All right, so with all of that preamble aside, let's get into looking at this example here, and then you can just do this for yourself. So I'll get back into this. Here's our statistics screen, ready to get started. Now the problem says the population in thousands. Now always be careful to read the question. So let's just remember the population is in thousands of bees in a particular colony increases as shown in the table. So we've got month versus population. I'm just going to go up here. You might notice in the statistics screen, you can actually rename your list 1 and list 2. So I'm going to call this one T. I'm going to call this one capital P. And I'm just going to enter in the data. So I've got month 1, month 2, month 3, and month 4. And then there's 36,000 bees in the first one, 38.75 in the second one, 42.5 in the third one, and 45 in the last one. Okay, so we've got our information there. Before we do anything else, let's just double check. That line and that button there is not ticked. Settings, it is set to a scatter plot, and we are drawing from list 1 and list 2. On this list here, when you want to set up a scatter plot, in your settings, in here, set graph settings, we're going to select draw is on, scatter is on, and for our X list, select whatever your list is. So if you don't remember if it's list 1 or list 2 and you've renamed it, that can help you. So I want T to be my X value and P to be my Y value. I'm going to set it like that. Now the first question says, plot the data points P versus T and suggest a model for the data. So let's see if we can come up with that. So we want to plot this. So what we can do is we can just click this button here. Now that we've set up the settings of the graph correctly, and then we have our representation. Now you would just eyeball this data, and you would say, okay, does this look like a linear line? Does it look like a quadratic? Does it look like a cubic? What does it look like? To me, it looks pretty likely it's going to be a linear equation. So I'm going to click Calc, Regression, Linear Regression. If it was a quadratic, I would click Quadratic Regression. I'm going to select X is T, Y is P. Click OK. It gives me an equation. So you would just copy this information down. So you can read here we have Y is equal to AX plus B, and it's given me values for each of those. So we just need to make sure that we get everything correct here. So first up, remember that Y is P. Then we have A is 3.075, and then that's being multiplied by T. And then we have plus 875. That would be our equation. Of course, the question is also requiring us to graph this. So in order to do that, we would just come up with our rough model. It doesn't have to be perfect. Ideally, you'd be using a ruler for this, of course. But we have here, this is our P, which is in the population in thousands. And then this over here is T, which is the number of months. And we would just put in our 4 data points like so, and we would draw a straight line that goes between them like that. So that's the equation of that straight line there, and you should also label the coordinates of each of these. So for example, this last coordinate on the side here, that's 445. And again, if you had a ruler, you could put these coordinates in a little bit more accurately. All right, so the question says, use the values when t equals 2 and t equals 4 to form a rule for the model expressing p in terms of t. So again, this time we're going to create a specific linear equation. This is not a regression line. Here we've been given 2 points. So of course we can form a linear equation that will pass through those 2 points. So a linear equation can always be formed if we have 2 points, and both of those 2 points will lie on the line. So let's figure out what 2 points we're using here. So we're going to use t equals 2. When t equals 2, p equals 38.75. And then we're also going to use t equals 4. So t equals 4, when t equals 4, p equals 45. So these are our 2 points that we're going to use. All right, so what the question's now asking us to do is to use these to form a model for p in terms of t. So what we want here is we want to find an equation of the form, well, it's a linear equation, right? So it's going to be of the form y equals mx plus c. I know there's a lot of letters here, but of course the y value here is the p, the population. The t value is going to be the x, so x value is going to be t. And then we have the gradient and the y-intercept. So we need to figure out what the gradient and the y-intercept are. So first up, to find the gradient, what we're going to use is we're going to use m is equal to, you might remember this formula, it's rise over run. And of course, instead of writing y2 and y1, x1, etc., we're going to use p's instead of y's and t's instead of x's. So that's going to be p2 minus p1 over x2 minus x1. All right, now we can just substitute in the values that we know. So let's just call this data point 1, this data point 2. So this will be equal to p2, which is 45 minus 38.75 divided by 4 minus 2. And then we can just use a calculator to work this one out. So I'll just go back to the main screen over here on the CAS. And then let's work out what this will be equal to. So that'll be 45 minus 38.75 divided by 4 minus 2, which is 2. All right, so we come out with an answer of 3.125. That's the gradient. All right, and now we're going to need to use that to figure out what C is. So step 2, find C. All right, so to be honest, we don't even need to find C here. We just need to find the equation. So you might remember that another form of a linear equation can be given by the point gradient form of the equation, which looks like this. So we've got the gradient equation here. I'll just write out another very useful equation that you should know, which is y minus y1 is equal to mx minus x1 for any point. So let's just continue using this point here. So we'll use this one as our point 1. Or maybe I'll use this one because it's got less decimal places. So I'll just put in p instead of y. So this is p minus, I'll keep 45, and just make sure that you use the x value associated with whatever y value you chose. So I'm choosing this one here. That's equal to the gradient, which we found was 3.125 multiplied by t instead of x, remember, minus 4. Okay, so we've chosen this point, we've substituted in those values into this equation. All right, and then what we just have to do is just simplify this down and expand this bracket over here. So we're going to end up with p is equal to 3.125t, and then we're going to have this times this plus this. So let's just work out what that is real quick. 5 times negative 4 plus 45. Okay, and that comes out as 32.5. I've just kind of skipped a step there, but for those of you who got lost there, all I did was I expanded this bracket. So that gives me 3.125t minus 3.12 times negative 4. which was negative 12.5, and then I added 45 to that, and then I got this answer here. All right, so that there is the equation, and that's the answer to B. So that is a model for P in terms of T. All right, so now the question says, if the variable T measures the number of months since January, determine how many bees were in the colony in January according to the model. So we'll always just take like the most recent thing as what we are looking at here. It's actually a little bit unclear which model they want us to use. Do they want us to use this model or this model? But it says, if the variable T measures the number of months since January, determine how many bees were in the colony in January according to the model. All right, so very first thing here, we're trying to work out the number of bees in January. But let's start by asking ourselves a different question. How many months have passed since January in January? So in other words, what will T be equal to? Well, considering we're in January and we're measuring since January, T at this point will simply be equal to 0. Just writing that might get you a mark for a question like this. All right, so then the next question is, which of these equations should we use? Let's just do them both, I guess. So in part A, we found this equation here. We found this one. So I think I can just copy paste that. Not sure how to do that. That's right. Let's just imagine I take, so this is the T value here. I substitute T equals 0 into this equation. The population will come out as, well, that times 0 just gives us 0. That'll give us 32.875 will be equal to P0. And if we look at model B, which was this one here, if we substitute in T equals 0, this just becomes 0, and it tells us that P0 will be equal to 32.5. So looking at these two equations, they're both roughly the same as each other. So it looks like, according to both models, there'll be somewhere around, I guess, 33,000 bees. But of course, we don't actually have data related to January. We've only started 1 month after January. So what we're actually doing here is we are extrapolating on the data because we're looking at data that lies outside of this range. So we're not completely sure about this prediction, but it's going to be somewhere around 33,000 according to these calculations that I've just done here. All right, let's move down slightly. It's a very last question here. The question's asking us to state the rate of increase in the population according to the model. Of course, it will depend on which model that you use. But general rule of thumb here is when we're dealing with a linear equation, rate is equal to gradient. And with your knowledge of calculus from last year, you'll remember that the rate is actually equal to the derivative of the function. And the derivative of a linear equation, y equals mx plus c, the derivative will actually just be equal to m. If you remember, dy dx is equal to m, because the derivative of a constant is 0, and this power counts down by 1, so that just becomes x to the power of 0, which is just 1. So dy dx is equal to m. So if we look at this, we need to state the rate of increase in the population of the bees according to the model. Again, it depends on which model that we use. If we're using model A, it's going to be this value. Sorry, it's going to be, where's model A? Here it is. So if we use model A, it will be the number multiplied by a t, so that is 3.075. Or if we're using model B, it will be 3.125. In either case, it's around 3.1, isn't it? So yeah, it's roughly 3.1. So let's just say roughly 3.1. Roughly 3.1 what? Well, let's think about it. So when we're talking about dy dx, we're talking about the rate of change in y with respect to x. So what we have here, that's, well, let's just substitute in y and x. So y is p in this case, x is t. So we can see here that what we're dealing with is the rate of change in population with respect to time. So we could say that this is roughly 3.1 thousand bees, because remember that's what P is, per month. Because remember, that's what T is. So change in P with respect to T. And that should be the answer to that final question. All right, that's all for this morning. I'll catch you guys in the next video. See you next time.